Hey everyone, my name is Gilberto Feliu from the Electrical and Computer Engineering Department of UNCC. And today I will be discussing my work on improving trajectory tracking for small UAVs in predictable environments. And of course, UAVs are unmanned aerial vehicles. Think about drones, right? So to start off, it helps to think about the kinds of situations these aircrafts encounter. So conditions can shift quickly. Think about wind gusts, some sensor noise that might confuse the control system, or sudden pressure waves from controlled explosions. Think of military application setting, right? And any one of these can push a UAV off of its path almost immediately, right? Something worth keeping in mind, though, is how easily a sensor noise can mislead the controller. When the estimator receives inaccurate state information, the controller will respond to the wrong inputs, which often amplifies the deviation. And on top of that, pressure waves behave more like an abrupt shove, an impulse. And the aircraft would have to recover almost immediately just to remain stable. Altogether, I'd say these disturbances create a clear need for the trajectory generation and control methods that can remain stable when the environment becomes unpredictable. With that perspective in place, it's helpful to look at how the control structure is organized. So, in this framework, the Crazyfly relies on a built-in geometric controller that generates forces and moments for trajectory tracking. And from a broader standpoint, the long-term goal is to allow that control layer to be replaced or supported by external controllers, and eventually by a reinforcement learning based supervisor that would choose these different controllers. These different controllers are uniquely tuned geometric controllers that are purposed towards certain circumstances. With that being said, before moving in that direction, though, the internal control pathway needs to be fully understood, including where each signal is generated and how it flows through the firmware. That understanding sets the stage for the contributions made so far. So, one of the main outcomes has been establishing a reliable minimum snap trajectory pipeline capable of handling sharper, more complex paths. Along with that, progress has been made in mapping the Crazyfly control chain, particularly identifying where the internal force and moment calculations originate. That information becomes essential when considering any future controller override strategy. And from there, a major part of the effort involved improving the trajectory generation process itself. Right? So, at first, generating long trajectories as a single optimization led to slow computation and occasional instability. To address that, the path was divided into smaller segments, each optimized independently and later combined. And by doing that, computation time dropped from about 41 seconds to roughly 17. And the segmented trajectories produced smoother tracking during aggressive maneuvers. Right? And so the next step involves locating the point in the Crazyfly firmware, specifically in controller Lee.c, C++ script, where the internally generated forces and moments are passed into the mixer. Once that point is identified, externally generated control inputs can be injected to override the native controller. And so, in the near term, this can be done through the Python API, but in the long term, full firmware level integration will allow seamless control switching and eventually reinforcement learning based selection. And there are still a few limitations that shape what needs to be done. To begin with, very long trajectories can overwhelm the Crazyfly data pipeline. In addition, disturbances in simulation are simplified relative to real-world conditions, and while the firmware structure has been mapped conceptually, the controller override mechanism has not yet been implemented. Finally, all testing to this point has been simulation-based rather than hardware-based. And so moving forward, the focus will be on completing the override pathway, validating performance on the physical crazy fly, and preparing the system for integration with our reinforcement learning-based supervisor. All right, so here we reach the end of it. Thank you guys so much for your time. Additional details are available upon request.